Okay. Yeah. Thank you for introduction. I really prefer walking around the stage and using this microphone. My name is Lee, and I'm from the Incheon National University in South Korea. Today I'm going to talk about the tutorial about how we can apply ASD. You know, the ASD is the most attractive research field in the ALD. But the most of the person from the academia, they don't know. They are very much focusing on the material, where we can deposit, where we cannot deposit. But they actually don't know where we can apply for the real semiconductor devices. You know, the burst of, not burst, like the re-attention to the ASD was coming from the edge placement error issue in the logic devices. And then in last couple of the months, I studied a lot because, you know, all of the fabrication process is not open to the public and an academia person because that is very much confidential. I have a lot of interview with the industry person. I searched a lot of the patent and I open resources, and then I made the slide. Probably some of the very much expert than me from industry, you pointing out, oh, that point is not very correct, but you are correct. So maybe I can make some mistake because I'm not a real expert because I'm working in the university. So you can leave your comment. I'm Lee. Actually, I was luckily promoted to the executive editor in last year from associate editor in chemistry material. I was the ALD program chair in the last year, Jeju Island. So I assume the most of the people already understand what ASD is, what is the main mechanism, what is the main fundamental behind of ASD. I'm gonna skip it because in last year, the year before last year, so you heard about that many times. So I'm gonna try to explain why we try to use the ASD for the semiconductor industry. So as you know, the main three devices, which is the logic and then NAND flash memory, and then the DRAM device is moving from the two-dimensional to three-dimensional. So because of that, but right now, we are now using two-dimensional based fabrication technology. I like the movie. This is exactly same to our nanofabrication for the semiconductor device. Patterning, etching out, again, repeat again. So this is the very much two-dimensional process. This is not very proper for making the three-dimensional devices. And then more than that, so we have to think about adoption of the EUV. EUV is a very much expensive technology. So the blue one is the portion of the fabrication cost only from the EUV. So we have to think about how we can save our fabrication costs by using this ASD technology for silicon device fabrication. So why ALD-based technology? As you know, semiconductor fabrication process is the most complicated process human made so far. Basically, 600 or 1,000 every sequence is used for making DRAM devices. So nobody wants to change one piece of the stone because the industry person, they are very much sensitive to change their process because they don't want to screw it up. Because the process is too much complicated. If they change the one piece of the process, it may influence a lot to the other processes. They don't have any option. Because of that, they are not like using the new material. They don't want to use the new process. So because of that, they always are trying to reinvent using the very reliable technology. So I say this is a technological recycling. So for example, think about high nitride. High nitride can be used for DRAM cat electrode, DRAM word line, NAND gate, metal gate, diffusion barrier, because the high nitride is the most promising and a real highly reliable metal ALD. They say this is a nitride, but they say always that this is a metal ALD. They don't have any option. There are a lot of the competitor to change the nitride, but that is only competitor, technological competitor. They always using most reliable material, most reliable process. So because of that, the ALD has been adopted to the DRAM device the early of the 2000, and then adopted for high K dielectric fabrication by Intel 2007. So it's been almost 20 years. It's a very highly reliable technology. So because of that, the ALD is a very reliable technology, and then they try to solve the problem with the patterning. They try to merge ALD, very well-known, reliable, and then patterning. That is the ASD. This is one of my very the favorite one. Burger is a very well-known food in America, and bulgogi is also very well-known food in Korea. They merge it. So this is how the ALD process birth. So let's think about the saving costs and realization of the three-dimensional fabrication. So this is the very common 6-step, the patterning process. They try to deposit, making a pattern by using photolithography and then etch it out. If you have selective growth, you can skip this 4 process. You can save a lot of money. This is the cost industry by using the EUV. If you increase the number of EUV step, the fabrication cost increases a lot. And then the second region is actually real 3D fabrication. So for example, this, let me see. Yeah, here. This is actually the deposition inside the NAND flash memory structure. So there is no way to make by using conventional photolithography and etching technology. We have to use the selective deposition. So, and also this is the major cost in deposition and then etching and then lithography technology. We have to save money and then we have to simplify the process. We have to realize the real 3D process. Okay, so let's talk about the research and technological trend of the ASD. So as you know, the surface and monolayer has been adopted for the very early study about ASD. So surface and monolayer is the organic molecule. This is the structure of the octadiecil triclosilane. It composes of the head group, end group, and then chain. And then by using this chemical modification, we can change the surface reactivity from reactive to the inert, then non-reactive. And if you want to, you can take a picture, and then you can send my picture to me. That is really appreciated. You can take a picture whenever you want. And then this is the polymer. Polymer is one of the very promising inhibitor. And then, so this is the one example. I performed this in the last year of my PhD course. I using surface monolayer ODTS to deposit selectively cobalt on silicon oxide. And then, so they're always looking for the better process compatibility because the surface monolayer is organic molecule. It's not very good for silicon device fabrication because there are a lot of the reasons for that. But the surface monolayer is pretty much large size of molecule. For example, ODTS is 2.7 nanometer. So we are talking about 2 nanometer technology. It's not actually the 2 nanometer, but it's around the 10 or 12 nanometer size of minimum feature size. So, and then low thermal stability, and then contamination after removal. There are a lot of the concerns to the silicon industry person. And also, as I told you, they really don't like uncertified material. Surface monolayer is pretty much a great and interesting material, but that is not very certified material for the silicon device fabrication. So think about that. This is the cross-sectional image of the silicon device structure. And then the package level is almost a 10 micrometer to the 1 millimeter. Back end of the line, bevel, it's almost the 16 nanometer to the 10 micrometer. And then middle of the line, 20 nanometer and then 30 nanometer. The real transistor fabrication process, if we are front end of the line, 12 or 20 nanometer, that is the really small scale. They don't want to use the organic molecule, which length is around like 5 or 4 nanometer. They don't want to use that. They cannot use it. So because of that, from the first research by Jeff and Angel from Argonne National Laboratory, 2013, they suggested small molecule inhibitor. At that time, they were not trying to have the selective deposition, but they trying to control their GPC by blocking their adsorption site. And then 2017, Audrey suggested the really interesting idea, the ABC process. Because Audrey is a very much expert in the plasma ALD system. The plasma is not very good for maintaining the inhibitor. So this is as a consequence, he had to use this ABC process because he had to use the plasma. After almost 1 year later, my group suggested, why don't we use the precursor as an inhibitor? Because the precursor is a very much process compatible material already adopted to the silicon industry. So we can use a lot of the different type of the bad precursor because we have to plug. So this is the reported self-assembly monolayer for ASD. So I summarize everything for your reference, and then we can move on. Polymer, if you want to, you can take a picture of that. And then self-assembly, the small molecule inhibitor. As you can see, recently all of the research trend is moving on the small molecule inhibitor. They don't want to have the self-assembly property. They really want to use the small size and easily removable. And then we have the precursor inhibitor table. Okay, let's move on to the background of the silicon devices. So today, I'm gonna pretty much focusing on the logic device, NAND, and then DRAM devices. And then as you can see here, the logic device is developed from the 1 transistor to 11 billion. That is too much, a really high density of that. Compared to the logic transistor device, so we are researching it, the DRAM density, because the memory device is determined by using how many capacitor or how many transistor, which is the floating gate transistor, put into the limited area of our chip side. So that is the most important parameter to improve the memory devices. That is a little bit different from the logic devices. So this is the evolution of the transistor in the logic, DRAM, and the NAND. This is the schematic drawing about transistor evolution. So as you can see, logic devices used to be a planar and a FinFET, and then gate all around the nanosheet, and then moving on to the CFET. So you heard about the CFET, NMOS and PMOS, stack on the NMOS and PMOS. And then transistor of the DRAM, planar, and a recessed channel, and a saddle pin, and a vertical channel. This is the main idea right before moving to 3D DRAM structure. And then NAND flash memory already move on to the 3-dimensional, 2D planar, charge trail layer, 3D DRAM. It's moving on to the high stack. And then this is the pretty much the big difference between the 3 different things. So as you can see, this logic device, so this is the transistor level. So there are 1 layer of the transistor in the logic devices. But this is the logic devices, they have to connect the 3 electrodes by using their complicated interconnect line. Because of that, volume portion of that is interconnect extremely larger than that of the transistor level. So most of the problem came from the interconnect for the logic. But think about this. This is a DRAM structure. Transistor here, 1 cell. DRAM is composed of the one transistor and then one capacitor. We say the one cell. And then, so this memory capacity is decided by the size of this capacitor. Most of the problem came from capacitor. And then this is the 3D NAND. Every single piece of this is the 1 bit. It's operated by the floating gate memory. It's a vertically fabricated. And then most of the things came from transistor and an interconnect. So more challenging the fabrication. Logic devices, interconnect is much higher than the transistor, but DRAM, capacitor transistor fabrication is higher than the interconnect. Then the flash memory, interconnect is much higher than the transistor. So let's move on to the potential application of ASD in the logic. So I put some of the implemented the application or maybe potential application. Potential application was suggested by a lot of the researcher. And then some point, I created my idea and then put into this potential application. So you heard about the FAB, fully aligned BI, which is the another name for the edge placement error solving solution. And they used to be self-aligned BR. Self-aligned BR means the BR is aligned to the top line, top MX line. But there are a lot of the trouble to make the parasitic capacitance because of the limited alignment error by using the photolithography. So they say, why don't we make another alignment top and bottom? Top and bottom. Because of that, they say the fully self-aligned via FAB. And then this is the FAB process. So deposition copper ILD and a recessed copper and then making the high K dielectric material and then deposit the ILD and then making a pattern, making it through the pattern from the M1 or maybe M0 or M0 and then M1 and then through the V1. So this is the image of the right after the recessing process. So they making the additional intentionally select. This is not the selective growth, but have the barrier of the dielectric. And they making the distance between this line and then the another line. But the problem is if you use the metal recess process, there are a lot of the additional problem, line flopping, contamination, or line resistance increase. Because of that, almost like 2017 or 2016, I don't exactly remember, but Intel suggested, why don't we use selective deposition of that? This is a conventional top-down approach. But if you have the selective growth, they say the DOD, dielectric on dielectric. So you have the copper and an ILD, and then you have the surface monomer or any inhibitor, and then making an additional growth on the dielectric. So you can have the more space between these Vx to the next Vx. So TSMC very nicely demonstrated this idea. They presented, so this is the additional selective growth on ILD, dielectric on dielectric. So the challenging point, this is the very famous application already implanted during the process. The challenging point, there are some lateral growth or selectivity loss. This is a selectivity loss or roughness problem. This is the roughness problem. So let's move on to reverse selective barrier metal, MOD, metal on dielectric. So as you can see, by decreasing down the size of the interconnect line in the logic devices, the resistance is increased because it's going to be very narrow, and then the volume of the diffusion barrier and a seed layer is already capped, so they cannot reduce down. So the idea for this reverse selective barrier metal is they have inhibitor on the copper, and then deposit the diffusion barrier, and then deposit the copper by using electroplating. Because there is no diffusion barrier on the copper, and then because of that, we can increase the conductivity between bottom MX line to the top MX line, the M0 or M1. So we can directly making an electrical path through this bottomless contact. So by using this one, so we can reduce down a lot the resistance. And this is the exact result. Sample monolayer, they use the sample monolayer, ALD tantalum nitride, and then they use the ruthenium and then tantalum. And then this is the applied material result. There's nothing between the M1 to the BR. There's nothing. So Professor Soo-hyun Kim's group at UNIS and then my group suggested the same idea. So why don't we have the diffusion barrier by using the zinc oxide and then directly grow the copper on the copper. So zinc oxide is grow on the silicon oxide like ALD, and zinc oxide is not directly grow on the copper. So we have a lot of the result. This is the DOD or MOD, and then ASD material cobalt deposit on the copper platinum, but not on the silicon oxide. So this idea is directly used for this application. And let's move on to the void and seam formation on the M0 and an M1 line. And as you can see, this is the M0 and M1 line. So because of ALD is a very much highly conformal film deposition, but that is a very problem for making via on very narrow line because we have very conformal. As a consequence, we only have this very small portion of the seam and a void inside the metal line. So this is the very much problematic in the really small via size. So to solve out the problem, the idea is ASD bottom fill. So we block or ILD line and then directly grow metal film from the bottom. So it doesn't look like a very much possible, right? But in our group, so we selectively grow on the ruthenium directly on the moly, but not on the silicon oxide. So if you keep growing the ruthenium, and then you can grow more from the bottom to the top. And then by using ASD and then ASE concept, so we successfully demonstrated real bottom-up growth with Samsung Electronics. So this is the very promising, but we have to study more about this. And then this is another idea, tone inversion. So, the tone inversion is a very much a conventional process to make the one pattern to positive pattern to the negative pattern after photolithography technology. So the process is, if you have this pattern, you deposit silicon oxide, and then CMP out, polish it out, and then remove the original pattern. So you can invert this original tone to this. But because trying to deposit silicon oxide by using ALD, there are a lot of the seam and then void formation inside of that. This pattern does not have very strong mechanical strength. So if you use the ASD, so you use the inhibitor right on the top and then deposit from the bottom to the top. Because of that, we can prevent out any seam and void formation. And then after that, we remove our original pattern so we can make a very clean and then rigid cone inverse silicon oxide pattern. So this is the real result from the Samsung Electronics. So, right now, most of the logic device company, they try to make the CFET, which is a complementary FET. So originally, this is the gate all around the nanosheet FET, and NMOS and PMOS. And it is going to the stack on that. So So this is the real structure of that. Looks like a very much complicated. And then to realize this fabrication, they had to use silicon and silicon germanium architecture growth and then selectively etch it out, trying to deposit. It looks like a real three-dimensional fabrication, right? So I'm not gonna try to explain every single detailed fabrication process right now, but I'm gonna point it out. This is some of the summary of my idea how we can apply ASD for the CFAB fabrication. Probably I think that some of the person from the industry, they already knew it. For example, if you have the silicon and silicon germanium stack and then making a hole, and then etching out a little bit of silicon germanium. And then we have to selectively deposit silicon nitride only to maintain this structure because these silicon germanium should be removed out later. So we have to have the bridge. And then also we have to have the selective architecture growth and then write on selective architecture growth of the silicon germanium. And then we have to selectively deposit a dielectric. And then selectively architecture growth of the silicon pulse pipe. And then so we need to have the ASD selective growth, the spacer, selective growth on the dielectric. So this is the very much obvious application of the CFAT. But so we have to think about, this is the structure of the channel structure. So we have to think about how we can make source drain contact. So the challenging point, there is no idea how we can make the three-dimensional contact for source drain. And then also there is no idea making M0 and M1 line by using the ASD. ASD should be very important for the CFAB fabrication, but there is no way to realize that right now. But we have a lot of the different types of the material combination and then the surface combination researches so far in the ASD process. We can apply that idea to realize this. Let's move on to the NAND flash memory devices. So as you know, this is a three-dimensional NAND flash memory fabrication process. Also making this ONO mode stack and then making a channel and then trying to deposit the word line and a bit line and then making the final structure of that. So this is the very much famous application by using ASD for the NAND flash memory. So as you can see, this is the one transistor, gate, source, drain, this is a channel and a trap layer. So conventionally, this trap layer was not discrete, discontinued. This is a very continuous layer, continuous silicon nitride layer. Because of that, there is a lot of the cross-talking. So from the mechanism of the NAND flash memories, all of the data is stored inside this trap layer by trapping electron inside of that. So because these silicon nitride is physically connected with each other, there is a lot of the cross-talking effect. So if you make this selective grown silicon nitride on it, so we can permanently prevent out any cross-talking process. So this is the real fabrication process. And we have ONO structure, making us some reset, and then trying to deposit silicon nitride deposit, and then etch it out, and then making a selective growth for the mask, and then deposit silicon, remove out the recess area. And then by using this, the fabrication process, we can overcome the cross-talking, the problem. And also, this is another problem. If you make the NAND flash memory, this is the very uneven high aspect ratio structure. Because the surface is very uneven, it is very difficult to fill with this line. This is the same process we suggested in the Tony version. So making inhibition on the top or the upper area of that, and induce the bottom growth from the bottom to the top. And this is the last part of the NAND flash memory. Oh, not the last part. Okay. And this is the very well-known three-dimensional NAND flash memory structure. All of the narrow lateral line is a word line, so it should be deposited by the tungsten ALD. But the problem is we have to increase the number of these steps a lot. This is the high step approach. But the problem is this is the cross-sectional image of the tungsten deposition. There are a lot of the seam and void formation. You can think about you try to deposit some nanofilm deep inside of high aspect ratio structure, but this is the deep, real inside in the lateral the direction. Because of that, if you have the perfect conformal deposition profile by using the tungsten ALD, so they should have this void and a seam formation of that. One exact solution to overcome this problem is we can deposit inside first and then fill side out. Like we induce the bottom up fabrication, but side out fabrication is very much necessary for NAND flash memory devices, but there is no solution of that. So we have a very initial idea for that, but that is a very critical because this is the high aspect ratio structure, and an inhibitor absorption density is not very well controlled because this is the additional inside the structure of that. So that is a very much challenging point. And move on to the implemented the potential application of the DRAM structure. So this is the cap fabrication, capacitor fabrication. So we have the deep high aspect ratio structure, deposit the bottom tinitride electrode, fill with the polysilicon, and then making a hole, and then try to deposit high K, and then try to deposit the top tinitride electrode. This is a very much common the DRAM cap fabrication process. The problem is, to increase the capacitance of the DRAM cap, we have to increase the aspect ratio more. So to make the higher aspect ratio cap structure, so we have to very much high etching profile, but that is very difficult because during this etching process, etching mask should be maintained on the top area. But that is very challenging because etching rate of etching mask is not unlimited. So because of that, there are a lot of the problem. So they suggested the new mask, right, from the Samsung Electronics, but still they have a lot of the trouble. There are some residue inside of the structure. So one of the idea is once you have the PL or amorphous, so this is the amorphous carbon, and then they make the so inhibitor right on this area, deposit ALD film only on the amorphous carbon etching mask. And they make the amorphous carbon. Amorphous carbon is not a very strong material. So they make the protection layer on the amorphous carbon and then trying to etch it out to the bottom. So this is some result from the Samsung Electronics. They selectively deposit something on film on the PL layer, and then they can make the PL much stronger. And then this is the conventional, the blanket etch step. And first of all, they try to deposit silicon nitride. This is the bottom electrode, bottom the pad. And then this is the ILD structure. And etch it out. If they have the misalignments on here, they have the defect on this and an etchy, different etchy profile. But inspired by FAB, you remember FAB, fully aligned via. So we can suggest this idea. So this is the original, and then this is the nitride, the metal area and the nitride. If you passivate this metal area, selectively deposit nitride on it, so we can have fully self-aligned via same things in here. And because this area is protected by selectively grown silicon nitride, so we can have this structure. Also, this is another approach. So we have to deposit some metal pad on the metal top, the metal load area. And then because of the limited the photolithography tool, so we can make the right alignment on here. And then as you can see, as you heard about that, if you grow the ASD on the top, the panel surface, we definitely have the overhang growth. So because of ALD growth is isotropic growth, so we cannot prevent the lateral growth. But for this idea, so we can actively use the overhang growth. We intentionally grow overhang, right? This is the inhibitor overhang growth, making a path instead of this photolithography and etching process. And a selectively deposit silicon nitride. So by using this idea, there is no misalignment error in here. And this is another idea. So because this capacitor is a really high aspect ratio structure, it doesn't have any strong mechanical property. Because of that, we have to have the filling material. For example, this is the filling material filled by silicon germany, but this is not electronic grade of silicon germany, but that is the fill with the silicon germany. But as you can see, silicon germany should be deposited through this very narrow area because we have to deposit bottom electrode, high K, top electrode. But if you block the support area by using inhibitor, there is no deposition of that. We have more area for the more opening area for the deposition of the silicon germany. So because of that, we can prevent any pinhole and a void formation inside of the DRAM capacitor. And then you may hear about the 3D DRAM. So right now, logic device already move on to the 3D CFAB. NAND flash memory already move on to the real 3D NAND. DRAM devices right now move on to the real 3D DRAM structure. So this is the historical evolution of that. This is the vertical gate structure, 4F square. And then this is the real 3D DRAM structure, another concept of the 2D zero capacitor structure. But some of the device companies trying to make this VSCAT, the approach. And then this is the schematic drawing to how they can fabricate it all 3D DRAM structure. So if you have selective growth, to make this line, you can have the ASD bottom fill and a high K, ASD high K on here, and an ASD electrode in the lateral capacitor structure. So this is some of the idea for the real 3D DRAM structure. And I made this ASD matrix table because there is not too many material used in the silicon industry. So mainly they sell silicon oxide, nitride, tinitride, aluminum oxide, and then copper, moly, lithium, tungsten. But recently they are key focused on the silicon carbon nitride or silicon oxynitride. Those materials are very useful for that, but no one researched about selective growth on these surface. And then you may realize that silicon and silicon germanium is the most important material to realize the real three-dimensional structure fabrication. But there is no report about selective growth on the silicon and silicon germanium surface. So that is the really important and then very impactful research. And then future inside, I have a few more minutes, future inside of ASC. So this is the seven, the challenging point. And we have to think about atomic and a molecular inhibitor, and then bottom fill and a side out structure, and then reliability for the commercialization 2D and 3D. So in the laboratory scale, we can selectively grow on the surface, but one small defect is very problematic for the logic device. We have to think about how we can do that. And then the fast screening inhibitor and a precursor. So far, a lot of the research are trying to test one by one, precursor by one, surface by one. but that is not very effective. We have to think about another way, overcoming geometrical the problem in the 3D and an inline methodology. So some of the researchers from the industry, they always ask me, hey, Professor Lee, what is the best way to measure selectivity in the inline? But there is no way over that. And then clean inhibitor and removable. I have a few slides to introduce our research group recent approach, how we can screen the inhibitor and a precursor very fastly. As you can see, all of the ASD process, it's two different selectivity. Two different selectivity means adsorption of the selectivity of inhibitor or adsorption of selectivity of the precursor or reactant. If you know the selectivity, that means if you know this precursor can be absorbed on this surface or not, this inhibitor can be absorbed on this surface or not. So we can say, oh, this inhibitor is used for this combination of the surfaces. But it takes a really time-consuming process. So we suggested the graph neural network, and then our word is graph neural network. I'm gonna skip it. And I collect all of the case. We can make a pattern, and then we can make the pre-trained model. For example, if you have a pre-trained model, if you put this guy, that pre-trained model giving an answer, oh, his age is 38. His hobby is singing. His job is professor, probably. And his marginal state is a single. This is the magic of the deep learning process. So we applied all of the precursor reactant and the substrate. And then we changed that to the graph neural network, GNN, and then changed to a vector, and then making a GNN model, and then making a pre-trained model. The great answer is we choose this paper result, and then we put all of the precursor, substrate, reactant, and temperature data on that. And we don't have any information about that in our pre-trained model. And we asked that, oh, hey, pre-trained model, our pre-trained model name is Ajin model. And then he make a right answer except everything except one, because that is the only tested the 50 degrees C. So that means if you have the one inhibitor, if you have the one precursor, if you put into those information into your deep learning model, you can say, oh, this inhibitor can be used for this process, this precursor can be used for this process or not. This is the very useful AI-driven ALD research for the future. I really want to make sure this is all material is a very much sensitive to the confidentiality. I have a lot of the interview and a discussion with the industry person, but they didn't disclose anything to me. I just asked that, oh, this is how do you think about this idea? And they said, yes or not. Oh, good, no. Okay. And then I got a lot of the research from the internet. And if you're interested in the very much fundamental of ASD, I recommend to watch my tutorial. But that is the Korean, but I suggested, I provided the English subtitle. Thank you.